Last thing what we discussed was about the titrations, specifically the acid-base titrations. And within that, we learned if you have a monobasic acid and monoacidic base, how the titrations will lead to various pH cases. Okay. Now, what if you have titration of now polyprotic acids? That means the acids which can give more than one H plus ions. And if that happens, how many times you will get the endpoints and what kind of color changes you would observe in these cases. Okay, so let's look into that logically. So first, the H2CO3 is a very weak acid. Okay, H2CO3 is a very weak acid. The Ka value for that is approximately 10 raised to power of minus 7. Ka2 value is 10 raised to power of minus 11. Okay, we are titrating 0.1 mole of 0.1 molar 10 ml of H2CO3 versus 0.1 molar NaOH of various volumes. Correct? So, as we did earlier, case by case, let's do the same thing here as well. The first case is when the volume is 0 ml. If the volume is 0 ml, then which means there is only acid present in the test tube. In that, we would have H plus and HCO3 minus, either in the test tube or a flask. This is Ka1. The contribution of H plus from Ka2 is extremely low because you can notice the value of Ka2 is very, very small, which we can ignore it. Hence, I can say that Ka1 will be mainly equal to H plus concentration into HCO3 minus concentration divided by H2CO3. Okay. I'm completely ignoring the second dissociation. If I ignore the second dissociation, I can say this is C naught minus C naught alpha 1, C naught alpha 1, and C naught alpha 1. Alpha 1 is the first dissociation of the acids here. So considering these two factors are same, I can say this is X concentration and X concentration. That divided by initial concentration, this is again a small value to ignore. I can say this is X square divided by C naught. Okay, X square divided by C naught. Why is that so? Because you can notice that here I can write it as C naught minus X, X and X. And this X is ignorant in front of C naught. Hence, I can write this X is equal to under root of Ka1 into C naught, which is equal to under root of Ka1 C naught. Ka1 C naught. I mean, this is the same formula we have applied for weak acid. And what is the formula for pH? If you recall, pH is equal to half of pKa minus log C naught. That is basically taking minus log on both sides. So, which is equal to 7 minus log of 0.1, which makes it K value as 8 by 2, which is 4. So initially we starting the we starting the titration with pH value as 4. This is where we start the titrations from. Now slowly we are adding NaOH. So let us take this as second case now. Second case is when the volume of NaOH added is, let's say, 5 ml. If we take it as 5 ml, what is the reaction that will take place? The reaction would be something like this. H2CO3 plus OH minus will happen to get this as HCO3 minus and H2O. This is the reaction that takes place, correct? And here you can notice that 0.1 into 10, which is the millimoles, and 10 into 0.1, that is the next millimoles here. This wasn't formed to start with, right? Sorry, not 10, here it is 5. I took it as 5 ml. So 5. So here it is 1 millimole, here it is 0.5 millimole. So you can see this is limiting agent. This will be 0.5 and 0.5 form, which you can clearly make out that I have a weak acid and a conjugate base salt. What has this become? An acidic buffer. So this combination has converted into an acidic buffer. So for this acidic buffer, how do we calculate the pH? So the pH for this acidic buffer will be equal to pKa1 plus log of salt by acid concentration. So what is the pKa1 value here? pKa1 value, you know, if you notice for this one is 7 plus log of salt by acid concentration. It is 0.5 divided by 0.5. So which makes it log 1, or this will become 7. Got it? So have you noticed that slowly from 4, this is where initially it started, and from 4 to 7 it is all buffer solution only. So gradually increasing as you keep on adding NaOH, it will start to increase gradually, and with this acidic buffer we have pH value as 7. So it is not a sudden increase, it is a very gradual increase. Next factor, let us see, is when the volume of NaOH is 10 ml. If it is 10 ml, right, this entire thing would be the same. Now here instead of 5 we have 10 ml. When you have 10 ml, neither this nor this is left. Only salt will be formed, which is 1 millimoles. 1 millimole, and H2O will not be there. Got it? Have you noticed this is a very particular case? Just try to recall from salt analysis. Sorry, salt hydrolysis. From salt hydrolysis, we learned one thing, that when you have a salt which also has an acidic part of it, we call it as amphoteric salts. So this is HCO3 minus is, you know, ampho amphoprotic, sorry, amphoprotic salt, which means it can act like a salt as well as acid. So for such cases, do you remember how do we calculate pH? pH will be equal to pKa1 plus pKa2 by 2. Sorry. It is independent of what is the initial concentration of a salt. You just have to take the average of these two values. Now taking the average, what do I get? This is 7 plus 11 by 2. So 18 by 2, which makes it 9. So for amphiprotic salt, we got pH now as 9. So from 7, it has raised to 9 here. Okay? Right. This is your third case. Now D part is when you have volume of NaOH added, clear? Is, let's say, another 5 ml you have added here. So that is 15 ml. When you do it for 15 ml, what would happen? Okay. So in case of 15 ml, you notice that here actually now the OH is in excess. So here this is 15. So if this is 15, now you would notice that this H2O will go away, and more importantly, you will have 0.5 millimoles left here and 1 millimole formed here. But we forget the fact that HCO3 minus is also an acidic part. So that will again react with OH minus, which is left over. And that will convert into CO3 2 minus plus H2O. So how much is this part now? This is 1 millimole. This is starting with 1 millimole. And this is starting with 0.5 millimole. Now OH minus is limiting. You will be left with 0.5 millimole. And here we'll have 0.5 millimole of carbonate. Now notice this has become again an buffer solution, acidic buffer. This is an acidic buffer. So for this acidic buffer, what will be the pH? So pH will be equal to pKa2 plus log of salt by acid concentration. So pKa2 is 11 plus log of salt by acid concentration is 1. So therefore pH is 11. So therefore, case D, we found that pH value is 11. Please check if everybody understood case D. Any doubt here? Right. Now, case E is when NaOH, when the volume of NaOH is, let's say, 20 ml. If it is 20 ml, then obviously these two reactions will be the same here. Let me copy that again. This will be the same reactions that will follow through. Okay. Except that here in the second case, basically here we have 20 ml. So 20 here. So 1 millimole will be left here. And here also with 1 millimole, it will make a reaction. So both 1 millimole will get consumed and you will have only carbonate of 1 millimole. You will have only 1 millimole left here. This is for only carbonate here. Okay. Now here I want you to derive along with me how to figure out the pH value of only carbonate ion. Okay, this is a very challenging question, everybody. Okay, check it out. Find pH of pH of only carbonate salt in water. You should know what to ignore in these cases, correct? You have to learn thoroughly what to ignore and what not to ignore, right? Imagine pK1 value given is 7, pK2 value is given as 11. Initial concentration of carbonate given is C naught. This much stuff is given to us and I need to derive what would happen. Now, check out step by step, everybody. Okay, step by step, what do we need to do? First, we know that carbonate does not have any hydrogen to release out. So it is not behaving like an amphoteric salt. So that case is gone. Now it is a pure salt ion. So it will only do salt hydrolysis, which means if we have carbonate here, so that is, let's say, CO3 2 minus plus H2O. We expect this to form HCO3 minus plus OH minus. This is the first thing we expect. Let us call this as KH1. Let us call this as KH1. Notice one by one here, everybody. Now this HCO3 minus is also, coming from a weak acid part. So this will also get hydrolyzed. So that will be KH2, which can be converted into CO3, sorry, H2, CO3 plus OH minus. Here also you can get OH minus. Just check what is the value of KH1, because apart of these two equilibriums, what are the other equilibriums which can exist? You know that HCO3 minus also has another part that is acting like an acid. So CO3 2 minus, this equilibrium will also be maintained in the solution. And H2CO3 on the other hand, which is formed, will also have an equilibrium with HCO3 with H plus and HCO3 minus. So which will be Ka2. Sorry, Ka1. Correct. Have you noticed something? If I use these two equations, correct, I would be able to relate KH1 is equal to KH1 into Ka2 here. That would be equal to Kw, isn't it? If you want, you can write it and check it out. KH1 is HCO3 minus concentration into OH minus concentration, that divided by CO3 2 minus concentration, that multiplied by H plus concentration into CO3 2 minus concentration divided by HCO3 minus concentration. Is this logic clear? So you can see these two will get cancelled. So what do we left with? Only left with, KW, correct? That's why I have written it. KH1 will be equal to KW. Similarly, I can write KH2 will be equal to KW by KA1. KW by KA1. Okay. Now notice what is the value of KH1, everybody? It is 10 raised to power of minus 14 divided by 10 raised to power of minus, how much it was? Minus 11. Correct. Because K2 value is 11 means PK2 is 11 means K2 is 10 raised to power of minus 11. And that is coming as 10 raised to power of minus 3. And here KH2 is coming as 10 raised to power of minus 14 by 10 raised to power of minus 7, which is 10 raised to power of minus 7. Now we can say something. Everybody, look into these two values clearly. This is 10 raised to power of minus 7, 10 raised to power of minus 3, which means, can I say that the second hydrolysis here is hardly contributing, isn't it? Because you can see the KH2 value is very low. That means this equilibrium going in the forward direction is very less likely to happen, which means this OH minus contribution is hardly observed. This you should be able to, mathematically prove it like what we have done it, and then you know why we are ignoring it. Clear? Now we know that why we ignore the second hydration here, because in JEE advanced questions you might be asked to do the second part also, right? You'll be asked to derive things in terms of second part. But here, because the values clearly suggest that this is hardly contributing, now we will derive a formula only on the first basis. For the first basis, we know the formula already. So for, you know, KH1 only, okay, existing, then pH formula, we know that pH is equal to half of pKw plus pKa2 this time plus log of C0. This is the same derivation we have done it before. So we will use that. Half of 14 plus pK2 value is 11 plus log of C0 value. How much was the initial concentration for carbonate? 1 millimole divided by total volume. Total volume is how much? 30 ml. Because 20 ml of NaOH and 10 ml of H2CO3. And putting this into the formula here, 25 minus 1.48. Approximately I can take it as 1.5. Because log 30 is approximately 1.5. Okay, so that will be 23.5 divided by 2. So how much we have? 11.75. Correct? This will be the pH approximately. Please make sure everybody is aware of, how to solve for uh, salts coming from polyprotic. This part is clear? Samyak, did you understand this, bacha? Right. Okay. Now taking this into picture, what we can say, how does the graph work? Check. If we are starting with, you know, uh, pH like this, so the graph typically goes this way. From here it started, let's say this is 4. From 4 it has started, it went through a buffer zone, it crossed a point here, right? And from there again it went into a new buffer zone. From there again it crossed a point. From there it went into a salt hydrolysis mode, and this is how it has started. And what are the points? Somewhere at the midpoint here we had salt hydrolysis, here we had neutralization point. Okay, and what are the points where it found? This was at pH 9, this was at pH 9, and this was at pH 11.75. So there are two equivalent points here. Okay. This one is the first buffer zone. This one is the second buffer zone. Okay. Buffer zone 1, buffer zone 2. Started with pH 4. This is volume of NaOH added. So far in JEE advanced questions or mains questions, they have only asked graphical questions. So just by noting the graph, you should know at this point what is existing and this point what is existing. This was the questions asked. Let's say at point A and point B, what do we have? I can say at point A, only HCO3 minus exist, okay, which contributes to pH, Clear? Next, at point B, only CO3 2 minus exist, which contributes to pH. Done? Here you will not be asked about which indicator to be used and all. Here the mainly questions will be revolving around what is the mixture at which particular areas. Okay. So if you take this BZ1 zone, what do we have? In buffer zone 1, we have, H2CO3 and HCO3 minus. That's how it is forming a buffer. Buffer zone 2, we have HCO3 minus and CO3 2 minus. That's how it is becoming a buffer. There are two endpoints. This is called equivalence point or endpoint 1, and this is read as equivalence point or endpoint 2. There is one JEE question I have attached at the end here, last one. This is the very, very good question, which is similar to that. This is something which you will try it at the end. Got it? It is on the same basis. Just a graph, a bit, what do you say, a confusing way of giving the graph. But if you understand, if you see the question thoroughly, you will be able to figure out what does that graph represent. Okay. Done. So I think the polyprotic cases are clear, everybody. Right. So this is a part we need to learn. I mean, whatever we have learned is about the titration part.
So can you
Now,
scroll up?
yes, Richa.
Done, sir.
Hmm. The next part, which is the last topic of ionic equilibrium, is understanding the terms solubility and solubility product. Solubility, by definition, it is about the number of moles that are dissolved in 1 liter of solvent to form a saturated solution. Okay, so how many moles of the solute that has been dissolved in 1 liter of the solvent to form a saturated solution? That is called solubility. For example, what I'm trying to say is this: AgCl is a white powder, white color powder, which when you add it to water, sufficient water, infinity here represents sufficient water, you will notice that out of that powder, a very small proportion will only get dissolved. Okay, a very, very small proportion will only get dissolved. By definition, the amount that got dissolved is what we call it as solubility. So let us say if I write the concentration of the dissolved AgCl, that is by definition called solubility. Understood? So here the solubility is represented as S. Just not to confuse with our regular acids and bases, we use the concentration term in this case as S. But one thing you need to realize, any salt, remember that any salt which is dissolved in water will 100% ionize, or it will ionize to the maximum, correct? So which means the same salt here, S, correct? Let's say it has been ionized by X amount. So that should form X amount of this and X amount of this. And since the concentration is lost here, I have to show the same thing at equilibrium here also. Correct? So S minus X. Is this equilibrium clear, everybody? Now, if I add both of them, what do I get? This part will get ignored. Okay, so AgCl solid is giving Ag plus and Cl minus, which is X and X. Okay, see, in most salt cases, okay, X tends to S. Why? Because anything which is a dissolved salt will always undergo 100% ionization. That means it will dissolve to almost the 100%. Hence, we can say X can be replaced as S. Okay, S can be replaced as S. Therefore, now we can say AgCl, AgCl solid is in equilibrium with Ag plus aqueous ions plus Cl minus aqueous ions of S concentration and S concentration. Okay. If I take this as equilibrium constant K1 and this as equilibrium constant K2, the result of these two is multiplication of K1 and K2, and that is what we call it as KSP. KSP, the equilibrium constant for this is what we call it as KSP. So KSP here, which is equal to, K equilibrium multiplied by AgCl solid concentration. Because if I write the equilibrium constant, it is products divided by AgCl. But AgCl concentration, we take it as 1 because it is solid. Because the activity of solids is always 1. Okay. So if I take that, multiplication of those two would be equal to 1. Okay. Just a second. Right. So if I multiply this part here, so what do I get? So this would be equal to KSP will be equal to Ag plus concentration into Cl minus concentration, which is equal to S into S, that will be equal to S square. Okay, so this is how we can write the solubility product. Here, S is represented as saturated concentration of salt. Saturated concentration of salt. Got it? That means you cannot exceed this concentration anymore. Because if it tries to exceed this concentration, obviously the reaction will try to go backwards. That means at constant temperature. And you know that ionization is always, an endothermic reaction. As temperature increases, as temperature increases, S value increases. That means more will get dissolved and KSP value will increase. KSP value will increase. Okay. So I hope all of you understood what is a basic definition of KSP here. Okay. Everybody, please check it out. Any doubt in understanding KSP or solubility? Please check. All of you are done writing? Okay. Check out this question. If at all we have calcium fluoride, which is also a sparingly soluble salt, you will be always writing the equilibrium in this form. So calcium fluoride solid, it is in equilibrium with aqueous ions. And if the concentration here, the saturated concentration is S, then this will be 2S concentration. In that case, the Ksp value will be equal to S calcium 2 plus concentration multiplied by F minus square concentration, which is equal to S into 2S whole square, which is equal to 4S cube. That will be equal to 4S cube. Okay, clear? Let me give one more example. In case if you have barium phosphate, that is also a sparingly soluble salt. Okay, barium phosphate PO4 twice. And if that is being ionized, it will become Ba2 plus of 3 moles aqueous plus 2 moles of phosphate 3 minus aqueous. So in that case, if this is 3S and this will be 2S, that is a concentration of barium 2 plus and phosphate. Hence, Ksp value now will be equal to 3 times of S whole cube multiplied by 2 times of S whole square. Correct? That is 104 S raised to power of 5. This is how we can calculate the Ksp values. Right, everyone? So given any sparingly soluble salt, okay, these are those salts which are not 100% ionized. Okay, for those kind of salts, we can always use this equilibrium. Now notice, what are the factors? The first factor I already told you, temperature. Dissociation is endothermic. As the temperature increases, more salt will get increased and Ksp value will increase. Pressure. If you have aqueous ions here, correct? If you have an aqueous ion here, and by chance, if at all you have any common ion added, common ion as in like HCl, Cl minus is a common ion. And because of the common ion, now what will happen? The reaction will move more in the backward direction. So when it moves in the backward direction, now the solubility of AgCl will decrease. Now you can see that initially the solubility was more. Now the solubility S2 is less. So S2 value will be less than S1. This is due to common ion effect. Clear? Next is nature of solvent. Nature of solvent as in, suppose if you have AgCl dissociated, I mean dissolved in water, if it is S1 and S1 initially, and uh, later you are adding sufficient amount of ammonia. So what will ammonia do? This excess amount of ammonia will react directly with Ag plus ions here. Okay, so this Ag plus ion and 2 moles of ammonia combine to form complex. So what is happening? Ag plus concentration is being drained out. If it is draining out, what is happened to this equilibrium? It will keep moving more in the forward direction. So now the new solubility will be way greater than that of original solubility. This is due to complex formation. So remember that complex formation always increases the solubility value, and common ion will always decrease the solubility value. Okay. Are these two factors clear, everybody? You can go through these equations and check. Next, see, mono salts, which means both of them are coming from monobasic, I mean single, single cation and single anion cases. So BaSO4, AgCl, AgBr, ZnS, PbS, PbSO4, all of them, one cation, one anion. So that is mono salts here. So you can see these are all the mono salts. Next, mono and di salts, which means cation is mono, anion is di. So like this, PbCl2, HgCl2, HgI2, ZnOH thrice, COH twice, and so on. Next, di and di, Hg2I2 kind. Di and mono, Ag2S, Cu2O, these kind. Mono and tri, these are the forms. Di and tri, these are the forms which we just learned. Barium's phosphate and so on. Okay, clear? These are the type of salts you will notice. All of these are sparingly soluble salts, by the way. As a salt is a very generic form, it is used when to represent the sparingly soluble form compound, because zinc hydroxide or copper hydroxide, they are not salt, they are basic compounds. But we use salt as a generic term. Okay. Now, let's notice this one. Whenever it comes to electrolytes, by definition, you know that there are two types, strong or weak electrolytes. If everything gets dissolved 100%, we call it as strong electrolytes. If the dissociation is not 100%, we call it as weak electrolytes. Okay. Now, electrolytes which does not give 0.01 molar and more concentration in aqueous solution, then we say they are sparingly soluble salts or electrolytes. So in our case, when we discuss AgCl, that is a sparingly soluble salt. Why? Because here, if you notice, AgCl solid, when I take, okay, as it dissolves in water, sufficient water, to get Ag plus aqueous plus Cl minus aqueous, and concentration is S and S. This S concentration has found to be way smaller than 0.01 molar. That's why we say it is a sparingly soluble salt. Okay. So by definition, when we use the word sparingly soluble salt, we expect that it should be very, very less amount. I guess this point is clear, everybody. Now, notice this one. Salts which are dissolved until they undergo 100% dissociation, then alpha value is equal to 1 and Ksp value is S square. S being the solubility, which is the concentration of dissolved salt, Ksp being the equilibrium constant or solubility product. Okay. And now notice Ksp of AgCl is 10 raised to power of minus 9 molar square, that is given to us. And if I take Ag plus concentration as 10 raised to power of minus 5 and Cl minus concentration as 10 raised to power of minus 5. If I multiply them, what am I getting? I'm getting the concentration is 10 raised to power of minus 10. So which means any concentration other than saturated concentrations, those are called, normal concentrations, and the product which we get is called ionic product. And if the ionic product overpowers Ksp value, then the reaction has to go backward direction, and such solution is called as supersaturated solution. And if IP value, that is ionic product value, is less than Ksp, that means the reaction will favor in the forward direction. The solution is still unsaturated. It might be taking more amount of salt to get dissolved. And when IP is equal to Ksp, then we say the reaction is at equilibrium, or we say the solution is saturated. Okay. So that's the difference between saturated, supersaturated, and unsaturated solutions. Now notice, if you want to find out the solubility of, sparingly soluble salt like AgCl, if Ksp value is given as 10 raised to power of minus 10, okay, then how do we figure out? We will simply write the equilibrium equation, that is Ag plus aqueous plus Cl minus aqueous. This is S and S. Ksp value will be equal to S square, or S is equal to under root of Ksp. Okay. that is equal to under root of 10 raised to power of minus 10, which is equal to 10 raised to power of minus 5 molar. This is the solubility of Ag plus. Okay, I mean AgCl. Correct. Similarly, you can do that same thing for the next two here. You can see Bi2S3 bismuth sulfide Ksp value is given. Find out the solubility. It's easy, everybody. Please do that once quickly. I will get some water. You guys can see that. So Ksp in this case, because you need to write the equilibrium such a way we can have two bismuth ions with plus 3 and three sulfide ions with plus minus 2. So this is going to be 2s and 3s. So Ksp will be equal to 2s whole square and 3s whole cube. That on multiplying will give you 108 into s raised to power of 5. So this will be the Ksp value. Right, beta. Everybody got that correct. So from here solving s is equal to 10 raised to power of minus 3. See, now come to this part that if you have a general case of Ksp, that is m and n are in equilibrium with m with plus y and n with minus x, then that will be, this will become xs and ys, and Ksp will become xs raised to power of x and ys raised to power of y. And here you can see x raised to power of x into y raised to power of y multiplied by s raised to power of x plus y. That will be the Ksp value. Okay, this is a generic formula, correct? Now notice when you have a common ion effect, how do we solve it? That is, if you have something like calcium fluoride Ksp solubility is to be figured out, but NaF is already there. NaF is a salt which is 100% ionized. And if the Ksp value is given like this, F minus is already present in the solution, then what it is? See, if calcium fluoride, it is in equilibrium with calcium 2 plus aqueous plus 2F minus aqueous, and here there is some solid substance which is added to water, and that is already, I mean initially before even dissociating, already there is 0.05 molar fluoride ions present. And then at equilibrium, right, then we can say, let's say this is forming some s amount and this will be s 2s amount, 2s plus 0.05. This is the concentration of F minus. Now I can say that s multiplied by 2s plus 0.05 whole square, that should be equal to Ksp. That is that which implies s into, now notice this one, before adding fluoride, if there is no fluoride present, what will be the Ksp value? Ksp old, that is when you only have calcium fluoride, so that will become Ca2 plus 2F minus. So this should be S and this should be 2S. So Ksp will be equal to 4S cube is equal to 5 into 10 raised to power of minus 14. So I can write this as 4s cube. I'll find out approximately 5 into 10 raised to power of, sorry, 0.5 into 10 raised to power of minus 15. If I take 4 to the other side, I'll get s cube is equal to 1.2 into 4 into 10 raised to power of minus 15. This is what I can write. So s will be equal to cube root of 10 raised to power of minus 15 by 8. So if I remove that, I'll get this as 1 by 2 into 10 raised to power of minus 5. So which is 5 into 10 raised to power of minus 6. Correct? So I hope all of you got this point. how to calculate the original solubility without common ion. Have you noticed something? Without common ion, originally this was the solubility. Matlab 10 raised to power of minus 6 or less. And if you have a common ion, the solubility should further decrease. Correct, beta? Now, can I say something that this 2s value in front of 0.05, isn't it very small value? So in most cases, this is what we will do. We ignore this solubility contribution from the salt given. Just like we did it earlier in the ionic equilibrium also, we will ignore this part. So as you ignore it, what do I get? I will get now S multiplied by 0.05 whole square. That is equal to KSP. KSP value, how much we are getting? 5 into 10 raised to power of minus 14. Got it? Sorry. Here I made a mistake, I guess. Oh, I had to get a 0.5. Should be 50, right? Hmm. Let me rewrite that part. So it is 50 by 4. 50 by 4, I can write it as 1 by 400. Or let me not write that way, because this will be anyway taking out to be the root here. So 12.5 here into 10 raised to power of minus 15 s cube. So s will be cubed root of 12.5 into 10 raised to power of minus 5. I just wanted to show that it is in the range of 10 raised to power of minus 5. It's not the exact value we require. Got it? So that means we can ignore this value of 2s here. So if you do that, now what is the solubility? Solubility will be equal to 5 into 10 raised to power of minus 14 by, this will be 5 into 5 into 10 raised to power of minus 4. So that will be 1 by 5 into 10 raised to power of minus 10. So which is equal to 2 into 10 raised to power of minus 11. Okay. Everybody clear on that?
Yes, sir.
So from the question, you should learn something, that before adding the common ion, after adding the common ion, how much is the difference of solubility you are able to notice. The solubility constant doesn't change. Kp value doesn't change. It is only the solubility which will change. The equilibrium constant will remain constant always. Let us do the same question again. Everybody, please try to do it with me right now. Again, a common ion of various kind. Sorry. If calcium hydroxide is given and it is present in a common ion of NaOH or calcium nitrate, in that case, how do we figure out? Let's see. First case, everybody. Calcium hydroxide is a sparingly soluble electrolyte. I'm not using the word salt just to confuse you. So it is an electrolyte basically. So it will give you 2OH minus aqueous. Initially, there is no calcium 2 plus, but OH minus is already present as per the given common ion. And at equilibrium, this might form S, and this will become 2S plus 0.1. So you can see S into 2S plus 0.1 whole square is equal to, what is the Kp value? 6.4 into 10 raised to power of minus 6, which clearly shows that 2s can be ignored here. Okay, so the value, Kp value is not very high, so we can ignore that value here. Hence, we will get S into 0.1 whole square is equal to 6.4 into 10 raised to power of minus 6. So S will be equal to 6.4 into 10 raised to power of minus 4. This is the new solubility. Done. See case B now. Case B is 0.1 molar calcium nitrate. Okay. Put the same equilibrium again. Put the same equilibrium again. So originally we have 0.1 molar calcium 2 plus and no OH minus. So at equilibrium, I can say this is S plus zero point 0.1 and this is 2S. And now what will be the Ksp? Ksp will be equal to S plus 0.1 multiplied by 2S whole square. So which is equal to 4S. And again, we can ignore that part here, which is S here. So as I ignore that, it is 4S multiplied by 4S multiplied, sorry, 4S square multiplied by 0.1. So that is equal to Ksp, which is 6.4 into 10 raised to power of minus 6. So S square is equal to 6.4 divided by 4 into 10 raised to power of minus 5. Okay. So this will be 1.6 into 10 raised to power of minus 5 or 16 into 10 raised to power of minus 6. Got it? So S will be equal to 4 into 10 raised to power of minus 3. Sorry, minus 4. Yeah. Here I wrote it wrong. 1.6 into 4 into 10 raised to power of minus 4s cube. Yeah. So it is 10 raised to power of minus 3. Yeah. Done. So these are the new solubilities, or obviously the original solubility without the uh, common ions have to be much lesser value, much higher value than 10 raised to power of minus 3. Okay. Everybody, I hope you understood how to work around with the common ions. Let's see, what if you have a simultaneous equilibrium? Okay, that means you have two sparingly soluble salts. Instead of one, you have two sparingly soluble salts. For example, calcium carbonate is present, strontium carbonate present in the same solution. Ksp of calcium carbonate, let us call it as Ksp1, strontium carbonate is Ksp2. Okay. When both of them are present together, the new solubilities are S1 and S2. These are the new solubilities with the common ions. Okay. So in that case, how do we solve it? Check it out. Calcium carbonate initially, let's say if this is S1, this will be S1. Here this is S2. This has to be S2. So obviously here we have to put it as S1 and S2. Here also I have to put that S1 and S2 because this is a common ion present. So what will be the KSP1? KSP1, or for our convenience, let me call it as K1. So K1 is equal to S1 multiplied by S1 plus S2. Similarly, KSP2, which we can call it as K2, is equal to S2 multiplied by S2, S1 plus S2. And have you noticed, if at all I multiply, if I add both of them, K1 and K2, that will become S1 plus S2 whole square. And S1 plus S2 is equal to under root of K1 plus K2. Under root of K1 plus K2. Okay. And from here, if I substitute this equation back, so what do I get? I will get this as S1 is equal to K1 by S1 plus S2. So S1 will be equal to K1 divided by S1 plus S2 is K1 plus K2. Similarly here, S2 is equal to K2 by S1 plus S2. So S2 can be written as K2 divided by under root of K1 plus K2. So this is how you can calculate S1 and S2. Everyone understood how to use the simultaneous equilibrium now? Right. It's easy. You just need to check out what to be written in the common and always utilize the relation for K1 and K2. That will make it more easier. Now, the next type what we can do is the effect of pH on solubility. Okay. So, if you have a solution, a buffer solution, or something like already existing acid or a basic solution, then how does that impact your salt? Okay. Let's start with this case. Imagine I have a buffer solution where the pH is maintained at less than 7. That means it is an acidic buffer. I mean, it's a buffer solution which is acidic. And now, what if I write something like calcium carbonate? Calcium carbonate is a sparingly soluble salt. If I take this salt, what are the equilibriums that it can show? First, calcium carbonate solid will maintain an equilibrium with calcium 2 plus carbonate 2 minus. Guys, let me remind you once again, when we studied, the starting part of acid base, I told you something about this. H2CO3 is a weak acid, correct? If this is a weak acid and if it loses one H plus ion, what does it become? It will become a strong base, correct? Strong base, in fact, is also a very weak acid. And this weak acid, if it is a weak acid, if it is giving a carbonate, it should become strong base. So can I say carbonate is a very strong base, isn't it? Everybody got this point? So if it is a strong base, it would be very, ready to react with any acid, correct? And if you're taking a buffer solution where there is an H plus ion present, because pH is less than 7 means H plus ions are present, don't you think this carbonate will immediately react? Understood what I'm saying? So therefore, this is the equilibrium that will happen. That is calcium carbonate, if it is in equilibrium with calcium 2 plus aqueous plus CO3 2 minus. The equilibrium constant for that is Ksp. But what would happen is carbonate will react with the H plus present in the buffer solution and convert itself into H3O minus. Okay. And you know that HCO3 minus is also still a strong. Check out here. It is still a strong base only. Since it's a strong base, it can again react with more H plus present in the buffer solution till it converts everything into HCO3, H2CO3. Correct? Have you noticed this equilibrium now? Let this be equilibrium 1 here, and here it is equilibrium 2 here. And you notice that this K equilibrium 1 is nothing but 1 by Ka2, and this K equilibrium 2 is actually nothing but 1 by Ka1. Correct? Because this is the reverse is the first ionization of H2CO3, and the reverse here is the second ionization of H2CO3. Correct? Now, everybody look into it. Add all the reactions together. Add After adding all of them, what do I get? I'll get this as calcium carbonate plus 2 moles of H plus is giving out calcium 2 plus H2CO3. So a new equilibrium is actually established. Okay, this we call it as K nu. So K nu will be equal to Ksp multiplied by 1 by K2 multiplied by 1 by K1, isn't it? Adding of equations is multiplication of the constants, correct? Therefore, so K nu, K nu can be written as calcium 2 plus multiplied by H2CO3 divided by H plus whole square. H plus whole square. So that is equal to Ksp divided by Ka1 into Ka2. Okay. Now listen up, everybody. Check out carefully once again. Okay. Listen. Imagine before, if there is no buffer solution, there is no H plus ions. Okay. This is something which I can only express theoretically. So you need to understand it directly without any mathematical proof or something. Just check it out carefully. First, what I'm saying, imagine calcium carbonate was originally in a ionized form. चलो हमने लिया 100 moles बेटा, एकदम सिंपल नंबर्स में समझते हैं. ओके, इमेजिन आई टुक 100 moles. इमेजिन करो इनिशियली सिर्फ 2 moles और 2 moles डिसोसिएटेड है. ठीक है बच्चा, we have only 2 moles and 2 moles dissociated because sparingly soluble salt है, so we do not expect anything more than that. Okay, later now you notice that these 2 moles are combining with another 2 moles of H plus to get these 2 moles. Correct, ये खत्म हो जाएगा, and these 2 moles again combine with another 2 moles to get these 2 moles. Correct. Is this point clear बेटा? अब क्या मैं कह सकता हूँ ये 2 moles है और तो ये भी 2 moles है, बराबर एवरीबडी. नाउ इसमें से कैल्शियम कार्बोनेट हैज लॉस्ट बाय 2 moles, so what should happen? Equilibrium will drive again in the forward direction. ली शैटलर्स प्रिंसिपल, प्रोडक्ट को हटाते जाओ तो रिएक्टेंट और प्रोडक्ट बनाएगा, बराबर. नाउ यू हैड 98 moles हियर, 2 and 2 हियर. करेक्ट, ये 2 and 2 था, दिस वाज 98 ओरिजिनली. अभी क्या हो जाएगा, दिस माइट बिकम 96 and this might become 4 and 4, and the equilibrium keeps on pushing it. जितना H plus है, it will keep on pushing it. Now this might become 94 and this will become 6 and 6, and this might become 90. Correct, and how much this will become? 10 and 10. Somewhere it will come and stop. Somewhere, let's say here it has become 75, so what will this become? 25 and 25. Probably this is where it will stop. Now it must have reached the new equilibrium. All of you understood this logic? Everybody, any doubt here? Sure, right? Now, use the wording what I'm using now. Check out the wording what I'm using. That's why I call this as the new solubility of calcium carbonate is S nu and S nu, because both will be almost the same amount. Correct? Both will be almost the same amount. Clear? देखो और एक चीज बताता हूँ. There will not be any residue of carbonate and bicarbonate. ऐसा क्यों? अच्छा, what is 1 by K2 value? You know K2 value is 10 raised to power of minus 11. तो ये तो almost 10 raised to power of 11 हो जाएगा. This would be 10 raised to power of 7. Do you think कोई residue रहेगा? Because the equations are extremely in the forward direction, you will not notice any residues here as well. That's the reason why the S nu value for both of them will be same. Okay, right. So in that case, what we can say, K nu will be equal to Ksp by K1 K2. Therefore, this will be S nu whole square divided by H plus square is equal to Ksp divided by Ka1 multiplied by Ka2. That implies S nu is equal to under root of Ksp divided by Ka1 into Ka2 multiplied by H plus ion concentration. So this is how you calculate the S nu. Okay. I want all of you to first go through this, understand the concept thoroughly, how I found the uh, new solubility. Please try to derive it on your own again. Please do it now. Everybody, let's put this into application. See how the questions are asked. All these are previous year IIT questions only. Let's see this one by one, how the questions have been asked and how to solve it. We need to find out the solubility of AgCN, a base AgCN, which is a sparingly soluble salt with a buffer solution of 3. Ksp value of AgCN is given, Ka value of HCN is given. So logic is the same question. So you start doing it, writing the equation AgCN. It is in equilibrium with Ag plus aqueous plus Cn minus aqueous. Then Cn minus aqueous is actually been combining with H plus, which is present in the buffer solution to give HCN. And if this is Ksp, then this will be 1 by Ka. So if I add both of them, so we will get this as AgCN solid plus H plus. It is in equilibrium to give Ag, Ag plus aqueous plus HCN. So this is the K nu. So K nu will be equal to Ksp divided by Ka. And K nu equilibrium is equal to, this is S nu and S nu. So I can write it as S nu square divided by H plus, that is equal to Ksp divided by Ka. So S nu square is equal to Ksp by Ka multiplied by H plus concentration. Hence S nu will be equal to under root of Ksp divided by Ka multiplied by H plus ion concentration. Hence the S nu value will be equal to under root of Ksp. Ksp value is 4 into 10 raised to power of minus 16, that divided by Ka value, which is 9 into 10 raised to power of minus 10, that multiplied by H plus concentration, which is 10 raised to power of minus 3. Okay. So what are we getting? 2 by 3 will come out here. And you can see this as root of 10 raised to power of minus 19 and minus 10. So 10 raised to power of minus 0.45. Correct? This is what we have. Clear? This can be written as 2 raised to power of 3 into 10 raised to power of minus 5 into 10 raised to power of 0.5. Okay, 2 by 3 into 10 raised to power of 0.5. Root of 0.5 is approximately 3.14 into 10 raised to power of minus 5. So if I take this, this will be very, very close to 2 times of 10 raised to power of minus 5. That will be the S nu value. Done? Everyone? I hope you understood. Anna, any doubt here?
No, sir.
Ayushi?
No, sir.
Saida?
No,
Could you
sir.
please respond? Right. So Diksha?
Yes.
Okay. Guys, let's start with the next one. Similar case again. This time there is no common ion like that, but you are keeping this already in a buffer solution of pH 9. So how do we solve it? This is just a common ion case. MgOH twice, solid. It is in equilibrium with Mg2 plus aqueous plus 2 moles of OH minus aqueous. Right. Now, this you can directly write as SNU, and here H plus is maintained at 10 raised to power of minus 5 always. Why? See, pH value of the solution is 10 raised to power of minus 9. Sorry, I mean H plus ion concentration. If H plus is 10 raised to power of minus 9 in a solution, which makes OH minus as 10 raised to power of minus 5. So in the solution, always it is maintained at 10 raised to power of minus 5. So whatever the OH minus which is coming out, that will always remain to be at 10 raised to power of minus 5. Hence we can write S nu multiplied by 10 raised to power of minus 5 whole square, that is equal to KSP, which is equal to 1, how much it is given? 1.82 into 10 raised to power of minus 11. So S nu will be equal to 1.82 into 10 raised to power of minus 11 divided by 10 raised to power of minus 10, which is equal to 1.82 into 10 raised to power of minus 1, or 0.182 molar. This will be the new solubility. Finished, everybody? Now, next look into this concept, which is called preferential precipitation. It's called preferential precipitation. I'll show you with an example here. Notice. Imagine I have a solution which contains zero point 0.1 molar NaI, zero point 0.1 molar NaBr, zero point 0.1 molar NaCl. All of them are present in the solution. And then I'm adding AgNO3 drop by drop. I'm adding AgNO3 drop by drop. Then over the time, as AgNO3 interacts with Cl minus, we might expect AgCl will start precipitating. If it is interacting with Br minus, you can expect AgBr to precipitate. And if at all with with I minus it interacts, it might become AgI. The respective KSP values are given for AgCl, AgBr, and AgI. This is the question. Now, what we are asked here is we need to find out what is the first one to precipitate, second one to precipitate, and what is the third one to precipitate. Okay. So this is the question here. So the question here is, okay, find the first, second, and third precipitates and respective concentrations of other ions. What will be the concentration of other ions at that particular time? Okay. So let us understand this part here. When it comes to AgX salt, solubility of AgX salt, you will notice that AgCl has more solubility than AgBr than AgI. How can we say that? Check out the KSP value. Higher the Ksp value, which means it is easy to get dissolved. So its solubility will be relatively higher. Okay, so I can say Ksp, solubility of AgCl is higher than AgBr, higher than AgI. Okay. So now, in that case, I can say, what will be the first, second, and third precipitate? Check out. Can I say that based on this point, the first one to precipitate is AgI because that has the least amount of solubility. So for a very small concentration of Ag plus only, it will start precipitating. Now let's see when will it precipitate. The first one here will be AgI has to be the first precipitate. So at what concentration? Check it out. Ag plus concentration multiplied by I minus concentration has to be equal to Ksp, which implies Ag plus concentration when AgI is precipitating. When AgI precipitates, what is the Ag plus concentration? It has to be Ksp divided by I minus concentration. So Ksp value is given 8.5 into 10 raised to power of minus 17 divided by I minus. I minus originally 0.1. Hence, when the Ag plus concentration is 8.5 into 10 raised to power of minus 16, you will see AgI will be the first one which is precipitated. Okay. And second, AgBr has to. So what about the concentration of other ions here? Since this precipitate didn't influence ICl minus and Br minus, Cl minus and Br minus at this point of time, even I minus at this point of time at the first precipitation is 0.1 molar. Now see about the second precipitate now. When AgBr is precipitating, AgBr has to be the second PPT. So if it is the second PPT, at what Ag plus concentration it will do? Ag plus concentration when AgBr is getting precipitated will be equal to its Ksp value by Br minus concentration. Okay. So now notice when you have what is the Ksp value of AgBr in this case, it is given as 5 into 10 raised to power of minus 13. That divided by AgBr concentration is 0.1. So it is 5 into 10 raised to power of minus 12. Okay. So at this concentration of Ag plus, now Br minus will start getting precipitated. Now what will be the concentration of I minus? See, I minus concentration when AgBr is precipitating will be equal to Ksp divided by how much is the Ag plus concentration at this point of time. So therefore, Ksp of Ag I minus is 8.5 into 10 raised to power of minus 17 divided by 5 into 10 raised to power of minus 12. Okay, so that is approximately 1.7 into 10 raised to power of minus 5 molar. So what have you noticed? That means when AgBr is precipitating everybody, I minus have been already consumed because I minus तो continuously हो रहा है. So this is what you need to understand. AgBr precipitate होने के लिए AgI is not stopping. AgI is still going on. Along with AgI, now you are getting AgBr to precipitate. Correct? AgBr is over top of AgI. Remember that. Okay, so I minus was 0.1 molar originally. Now it has become 1.7 into 10 raised to power of minus 5. While Cl minus and Br minus at this point when the AgBr concentration is precipitating is still 0.1 molar. Now the third case when AgCl has to be the third precipitate, has to be the third PPT. So at this time, what is Ag plus concentration? Ag plus concentration which AgCl is getting precipitated, that has to be Ksp divided by Cl minus concentration. So Ksp value for this is 1.7 into 10 raised to power of minus 10 divided by divided by 0.1. So which is 1.7 into 10 raised to power of minus 9. This is the concentration of Ag plus. At this point, what is A minus concentration when AgCl is getting precipitated? So it has to be Ksp divided by Ag plus concentration when AgCl is precipitated. So that is equal to 8.5 into 10 raised to power of minus 17, that divided by 1.7 into 10 raised to power of minus 9. Okay, so that is coming approximately 5 into 10 raised to power of minus 8 molar. Similarly, what is the Br minus concentration here? So Br minus concentration of when AgCl is precipitating, it will be Ksp divided by Ag plus concentration when AgCl is precipitating, which is equal to 5 into 10 raised to power of minus 15, which is the Ksp of AgBr, by 1.7 into 10 raised to power of minus 9. And that is coming as 3 into 10 raised to power of minus 4 molar. Now, this is the standard question that is being given, that what is the concentration of I minus, what is the concentration of Br minus when AgCl is precipitated. So remember, these are I minus and Br minus concentrations when AgCl starts to precipitate. Okay, so please go through the question once, everybody. Check if you have any doubt, you can ask me. Everybody clear? Right. Before going into polytropic acids, because we have done that bits and pieces already, let us come to some important questions, how we can solve regarding Ksp values. Check. These are quick questions. All of them are PYQ questions. Right. Let's see how they have been asked, how to solve. Let's start with this first one, everybody. If you already have the pre-notes, you can directly go to this question, everyone. Check what is the solubility of FeOH thrice in the solution where POH is 8. That means OH minus concentration is fixed here. So the OH minus concentration here is 10 raised to power of minus 8. And you know that FeOH thrice, as we expect, it will ionize into a very small amount of Fe plus 3 and 3 moles of OH minus. So if this is S, this has to be 3S, or in this case, there is no 3S, it is already fixed amount, which is 10 raised to power of minus 8. So hence you know that S into 10 raised to power of minus 8 whole raised to power of 3 should be equal to Ksp. In this case, it is given 1 into 10 raised to power of minus 36. So solubility will be equal to 10 raised to power of minus 36 by 10 raised to power of minus 24. Got it? So that makes it 10 raised to power of minus 12. So that is the solubility of FeOH thrice. So I guess that is easy one. Everybody must have got that. Right. Let's go to the next question. This was again a PYQ which was asked about simultaneous solubility. If you have AgSCN and AgBr, so in that case, what will be the simultaneous solubility of AgCN and AgBr? To be honest, we can directly use the formula also, which is S1 into S1 plus S2 is equal to KSP1, and S2 into S1 plus S2 is equal to KSP2, and S1 plus S2 will be equal to S1 plus S2 whole square will be equal to KSP1 plus KSP2. That implies S1 plus S2 is equal to under root of KSP1 plus KSP2, or simply S1 by, sorry, S1 is equal to KSP1 by under root of KSP1 plus KSP2. So let's substitute these values. What do I get? So it is 1.1 into 10 raised to power of minus 12 divided by under root of 1.1 into 10 raised to minus 12 plus 5, or we can just put it as 50 into 10 raised to, sorry, I can simply write it as 5 into 10 raised to power of minus 13, which I can get it as 1.1 into 10 raised to minus 12 divided by, I can write this as 0.5. So 0.5 will become 1.6 here. So this can be written as under root of 1.6 into 10 raised to power of minus 12. 1.6 into 10 raised to power of minus 12. Okay. So hence S1 will be equal to 1.1 divided by root of 1.6, that into 10 raised to power of minus 12 by 10 raised to power of minus 6. So 1.1 divided by root of 1.6 into 10 raised to power of minus 6. So this is the new solubility. Likewise, if you notice S2 will be equal to KSP2. KSP2 is 5 into 10 raised to power of minus 13 divided by under root of 1.6 into 10 raised to power of minus 6. So which is 5 root by 1.6 into 10 raised to power of minus 7. So that is a new solubility S2. So this is S2, this is S1. So this is the solubility of AgSCN, and this is solubility of AgBr. These are the values. So I think you know how to solve it. Okay. Now, notice how to make the same question into little bit more complex. Same question, but this time with a little bit more complexity. That is, F, again we are using a simultaneous equilibrium. We are trying to figure out what is the F minus concentration in MgF2 and SrF2. Okay. So it is also a simultaneous equilibrium, everybody. Let's see how we can solve it. So write this as MgF2 solid. It is in equilibrium with Mg2 plus 2F minus. So if this is S1, let us say this is 2S1. And on the other side, if it is SrF2 solid, then let us say this is going to be Sr2 plus 2F minus. So this is S2 and this is 2s2 plus 2s1. Here also it is 2s2. This is the concentration. So I can say that Ksp1 is equal to S1 into 2s1 plus 2s2 whole square. And here Ksp2 will be equal to S2 into 2s1 plus 2s2 whole square. What if I multiply these two? So it will be Ksp1 and Ksp2. I mean, if I add both of them, I'll get this as S1 plus S2 multiplied by, if I take 2 common, I'll get 4 into S1 plus S2 whole square. That implies 4 times of S1 plus S2 whole cube is equal to Ksp1 plus Ksp2. And F minus concentration is 2 times of this, isn't it? So first if I multiply, first if I multiply S1 plus S2 and then multiply that with 2, I'll get that value. So let's do that. S1 plus S2 whole cube is equal to Ksp1 plus Ksp2. Ksp1 plus Ksp2 is 9.5 into 10 raised to power of minus 9 plus 4 into 10 raised to power of minus 9, and that divided by 4. Okay, and if I just take the root of here, so I'll get S1 plus S2 is equal to 9.5 plus 4 divided by 4 into 10 raised to power of minus 9 whole raised to power of 1.1 by 3. Got it? So that will be 1 by 3. So that is going to be 13.5 by 4. So 13.5 divided by 4 into 10 raised to power of minus 3. Got it? So this value, if at all I multiply this with, sorry, this also has 1 by 3. Yeah, 13.5. Let me just do that calculation part. 13.5 divided by 4, 3.375. So cube root of, 3.375 multiplied by 1 divided by 3. So that is coming as exactly 1.5. So 1.5 into 10 raised to power of minus 3 is what we are getting. Now we got this one. We require F minus concentration. So F minus concentration is simply 2 times of S1 plus S2. So that is equal to 3 into 10 raised to power of minus 3. That is the final concentration of F minus. So note it. Everybody, please check if you have understood that, how to solve it. See the next one. Calculate the AgI concept, solubility of AgI in 0.01 molar KCN, and instability constant of AgCN twice is given. Okay. What is K instability and what is K complex formation? Let me first explain you that. For example, if you have Ag plus 2Cn minus, it is forming a complex like AgCN twice with minus here. Then the equilibrium constant for this is called as Kf or K formation. This is called K formation. But if I put the same thing in a reverse order, that is Ag Cn twice minus, it is in equilibrium with Ag plus 2 Cn minus, then this is called K instability, right? So this is K instability. So one is K in. If you use the terminology K in, that means we are talking about instability. Kf means we are talking about K formation. So we need to figure out what is the solubility, molar solubility of AgI. So let's do that here. So we have AgI, it is in equilibrium with Ag plus aqueous plus I minus aqueous. Okay. And now the same AgI is being treated with Cn minus 2 moles. So that will be converting into AgCn twice minus. And if this is Ksp, this is K formation, correct? K formation is 1 by K instability, right? So therefore, if I add both of them, so what do I get? I'll get this as AgI solid plus 2 moles of Cn minus. It is forming AgCn twice minus plus I minus. And what did we learn earlier? If this is S nu, this will also be S nu, correct? And what is the equilibrium constants here? Ksp multiplied by K formation, which is nothing but Ksp into 1 by K instability. And therefore K nu, which is equal to S nu square divided by S nu square divided by Cn minus concentration, which is 0.01 molar. Okay. Hence, I can say this is 0.0101 molar whole square, that is equal to Ksp divided by K in. And Ksp is equal to 8.5 into 10 raised to power of minus 17. That divided by K instability, which is 1.9 into 10 raised to power of minus 19. Finished? So check out what is this. We have S nu square is equal to 8.5 divided by 1.9 into 100, and that into 10 raised to power of minus 4. Okay, so S nu will be equal to under root of 85 divided by 19 into 10 raised to power of minus 2. That's it. Sorry, not minus 2, minus 1. After taking the root, it will become 10 raised to power of minus 1. And this is coming approximately 2.1 into 10 raised to power of minus 1, or 0.21 molar concentration. So please check this out, everybody. Any doubt here? All good? Right, everyone. Let's go to the next one. Check out this one. How much AgBr can be dissolved, assuming this is the only complex form? This is exactly like we have done it earlier now. K formation is given. I don't think anything required from this solving. You have to try it on your own. Okay. I'll give you 2 minutes. Try it. AgBr, it is in equilibrium with Ag plus aqueous plus Br minus, while here this is case P. You know that Ag plus 2 moles of NH3, that is also making an equilibrium. I mean, making a complex formation as twice with plus here. For this, it is case P and this is K formation. If I add both of them, so I will get the new equation here, which is AgBr plus 2 moles of ammonia. It is in equilibrium with complex plus Br minus, and it will be Ksp into Kf, which is the K nu. So K nu will be equal to, this is S nu whole square divided by ammonia square, that is equal to Ksp, which is 5 into 10 raised to power of minus 13 into 10 raised to power of 8. These are the values which are given. So which is 5 into 10 raised to power of minus 5. So S nu will be equal to 5 into 10 raised to power of minus 5 multiplied by ammonia square. Sorry, this is square only. S square is equal to how much is the ammonia concentration given? 0.4 molar. Yeah. So 0.4 whole square. 0.4 whole square. Let me take the root directly. Can I write this as 50 into 10 raised to power of minus 6 into 0.4 whole square? Can do that. So on writing that, we have an advantage. Now I can directly take the root. So root of 50 is almost 7. So that into 10 raised to power of minus 3 into 0.4. Okay. So this is 2.8 into 10 raised to power of minus 3. This is the concentration nu. Okay. Now tell me what is the old concentration. That is, if there is no ammonia present. So if there is no ammonia present, Ksp, only Ksp will be equal to Ag plus concentration into Br minus concentration, which is equal to S square. So S would have been simply equal to under root of Ksp. So under root of Ksp value will be equal to uh, Ksp is how much? 5 into 10 raised to power of minus 13. So which is, I can write it as root 50. Root 50 I can take it as 7 into 10 raised to power of minus 14 means minus 7. This is the value of S old. S old or only we have. Now it is been asked that how much AgBr could be dissolved in it. This much dissolved in this one. Okay. How much AgBr could be dissolved in here? Correct. So you can notice that in 0.4 molar. I mean, this much is the amount of AgBr that got dissolved. This is the old one. Okay. So you can see, even if you check out new minus old, correct? This is the extra amount that got dissolved. So you can see the old is almost ignorant. It is only this mole, this concentration which is being added. I guess this is understood. Yeah. Clear, beta? This is particularly asked multiple number of times. Okay. Now this question is asked multiple number of times. Notice this one. Minimum moles of ammonia required to add 1 liter solution so as to dissolve 0.1 molar AgCl by this equation. Minimum moles of ammonia is a very standard question. Minimum moles of ammonia. See, from the above thing, I'm directly writing the equation, what we know, that is AgBr plus 2 moles of NH3, correct? It is in equilibrium with Ag NH3 twice plus Cl minus. Sorry, instead of AgBr, it is AgCl here. Yeah, AgCl here. Okay. Now, this one is 0.1 molar. Okay, moles, because volume, these many moles are given. Let us say A moles is the minimum moles of ammonia required before the equilibrium, and AgCl will get completely over as it get dissolved. So A minus 2 times of 0.1 moles has been lost. So that should give you 0.1 and 0.1. This much is the value that must be followed. And for that, what will be the K nu here? K nu will be equal to Ksp multiplied by K of formation. Okay. So you can see K formation, Ksp both are given 10 raised to power of minus 10 into 10 raised to power of 8. So that is equal to 10 raised to power of 2. Hence, we can write 0.1 whole square by A minus 0.2 whole square. That is equal to 10 raised to power of 2. Right? This is K nu. So which implies take root on both sides. So I'll get 0.1 by A minus 0.2 is equal to 10. Sorry, not 10. 10 raised to power of minus 2. So 1 by 10. So 1 by 10. Right? So that is equal to 1 is equal to A minus 0.2. So A has to be how much? 1.2 moles. So very, very standard question, everybody. Please check it out how to do that.